Hi, folks. This lecture goes with class on Tuesday, the 14th of April. The topic is an introduction to nonlinear systems of differential equations. We're in section 16 of the notes and section 5.1 of the textbook. So before we begin talking about sort of new topics here, I thought we would pause and sort of think about where we are. In particular, I want to think about where we are in terms of what kind of differential equations we can solve with analytic techniques. So here's what we can do so far. We can analytically solve separable differential equations. So that's a first order differential equation, which can be written as a product of a function of y and a function of t. And we know how to solve this and have known how to solve this for some time, as long as you can actually take the integrals that are involved in solving it. The second type of differential equation that we learned how to solve analytically was a first order linear differential equation. So this was a differential equation that could be written in this format as a linear combination of y and a constant term, or sorry, not a constant term, but a term that just depends on t. And we know how to solve this, again, provided you can either do a good job of guessing and checking, or you can compute the actual integrals that show up in its solution. The third type of equation we know how to solve analytically is this guy, our plain old linear system. And that was a big topic for us maybe a couple weeks ago. So we know how to solve this thing. Turn the phone off. And then finally, we used those linear system solving techniques to solve second order linear differential equations. And most recently, we've added the wrinkle of adding some forcing to these equations. Okay. So this is great. We can solve these equations. Many of them have important applications to physics, econ, biology, other things like that. The problem, though, is that these sort of equations represent just a tiny fraction, maybe epsilon percent, of all the differential equations that could possibly be written down. Right? You'll notice here that nothing is going on with squaring the value of y or taking a square root of the value of y. There's no cosine of y prime. There's no e to the y. There's nothing involved with combining y and its derivatives in any ways besides just taking a linear combination of those things, with the exception of the separable differential equations. And those have to have a very particular formula where the y and t parts can be separated. Now, there's a little bit of good news in that important differential equations often fall into one of these categories. But again, of all the different differential equations that you might want to solve in a real application, let's say maybe 2% of them are going to happen to match one of these very particular patterns. So what this means is that although we've become quite good at solving different types of differential equations with our analytic techniques, this is only a small amount of differential equations that we can apply those techniques to. Luckily, we have some other ways of approaching these equations. We have a qualitative toolkit. We can study them qualitatively by doing things like looking for their equilibria, and classifying them. That often gives us really important information about the solutions to these differential equations. We have graphical techniques. Slope fields or direction fields can give us really nice qualitative information about the solutions in a graphical manner. And then we have an important theorem, the existence and uniqueness theorem, which in particular tells us that solutions can't cross, at least in the phase plane. And we'll talk a little bit later in these section of lectures about ways that that can be especially useful. And then we also have Euler's method. This is part of our numerical toolkit, and it can be used to create approximate solutions. Although, as we've learned by now, you have to be careful about how you use it. Sometimes Euler's method can lead you astray if you're not thoughtful about the situations in which you're applying it. And that goes not just for Euler's method, but also for fancier numerical methods as well. All the rest of the differential equations, the other 98% in my sort of rough estimate here, are nonlinear differential equations. So our goal for the rest of the semester is to use our linear methods, our linear analytic methods, as well as our qualitative toolkit and our numerical toolkit to study these nonlinear equations. And even if we can't fully solve them, even if we can't write down specific solutions, we'll still be able to say important things about what happens with the solutions of these differential equations, important things that can help you when you study their application to other fields. All right, in the next video, we'll look at a first example of a really important and interesting nonlinear differential equation, and we'll think about why it's nonlinear.